Hello everyone, hope you are doing well, healthy, and coronavirus free. My name is Benjamin Soraghi from University of Akron. Me and my advisor, Dr. Huang, uh, worked on corrosion and how corrosion affects the bonding between rebar and concrete in structures. The title of this presentation, as you can see, is Probabilistic Model for Rebar Concrete Bond Strength Prediction with the consideration of corrosion and bond failure mode. So because there are not many sessions in this conference that related to corrosion and structures, I'm going to have a few slides talking about the introduction of my research related to corrosion and structures. One of the important consequences of having corrosion is that it is costly. The cost of corrosion is so tremendous that the total annual cost of corrosion is around $1 trillion. But regarding the structural consequences, corrosion deteriorates the performance of the structure. And by performance, I mean reducing rebar diameter, yield strength, ductility, and most importantly, it deteriorates the bonding between rebar and concrete. So when the bond deteriorates, two important characteristics of a structure get affected, and those are the bond strength and the bond failure mode. The bonding is important because, as I said, it ensures the reliable performance of the structure. Bonding is, though, affected by properties of a structure such as rebar diameter, rib spacing, concrete cover, confinement index, and concrete properties like F prime C. But what I meant by bond failure mode, it has been shown that when a structure reaches to its maximum capacity, there are two ways that it can fail. There are two modes that the failure happens, which are known as pull-out failure mode and the splitting failure mode. Pull-out failure mode is when the failure happens in a relatively flexible way, as you can see in figure A, and the splitting failure mode is when the failure happens in a sudden manner, as you can see in figure B. So in summary, corrosion results in cracking and, more importantly, deteriorating rebar and concrete bonding, and that will result in changes in bond strength and bond failure mode. Here I put pictures of specimen happen to be pull-out, having a pull-out and a splitting failure mode. You can see this is the pull-out failure mode and this is the splitting failure mode. And here on the right, you can see the difference between the behavior of having pull-out and splitting failure mode. You can even see that we have different values for bond strength for each failure mode. So people in the past have worked on bond strength, but how the bond failure mode influences the bond strength and the structural performance is not really well investigated. So in this research, we try to develop a probabilistic prediction model for bond strength that also considers corrosion and bond failure mode. Here is the outline of the things that I'm going to talk about next. First, I'm going to talk about our experimental work. Then I will explain the approach for the model development. And at the end, I explain the case study of an RC beam. And then I will talk about the summary and the conclusions. The way that we did our experimental design is that we constructed 3 batches of concrete with 3 different F prime Cs, 27, 36, and 43 megapascal. Then each batch includes specimens with various ranges of cover size, rebar diameter size, corrosion level, which ranges from 0 to 20%, and different transverse confinements, and also both monotonic and cyclic loading. Here on the right side, you can see the schematic view of the specimen design with the configuration, which is mostly adopted from a STM standard. In this slide, you can see how we actually constructed the specimens. First, we made rectangular, same-sized forms that comply with the parameters that we adopted, that we talked about in the previous slide. Then we prepared the rebar. Then we added the concrete, which was salted. And then after casting the specimens, we had to corrode them. But it was not an easy task as we thought. We faced some challenges. One is, as you know, corrosion is a very time-consuming phenomenon, meaning in real life, it happens in the course of years, but we had to do it in the course of weeks. Second, we needed to provide a very humid place for all the specimens, because otherwise when concrete dries out, the dryness deaccelerates the corrosion process significantly. Third, which is also very important, is that the current that goes through the rebar fluctuates very dramatically as the rebar corrodes throughout the whole process. The last, but definitely not the least, was the localization of the corrosion on rebar, meaning corrosion does not happen uniformly throughout the rebar and accumulates locally. The solution that we adopted are as follows, and I'm going to explain them. Well, for the time-consuming process, the issue of having time-consuming corrosion, we used the acceleration process, as I said, using power supplies, as you can see in the right corner, the picture. For the humidity, we constructed some humidity tents that isolate vapor inside the tents. And for the third problem, that is current constantly changes, we used light switches. We used actually 3 techniques. First, we designed a parallel circuit that provides us with a constant voltage. Parallel circuit makes it harder to monitor the current, but requires much fewer power supplies to produce the voltage. And finally, we solved the problem of monitoring the corrosion by installing some light switches to the specimen, to each specimen, that they have on and off switch. So we can turn it on, turn it off, monitor it every day, and we know we were able to track the corrosion process by knowing the fact that how much current every day they went through, each specimen went through, so we know what's going to be the estimation of the target corrosion. In this slide, you see the experiment setup. On the top right, you see the schematic design of the setup. Then below it, you can see the actual testing frame. Note that there is a force end and a free end. The force obviously is applied to the force end, and the displacement is recorded from the free end, because it is the free end that gives us the bond slippage. Also on the left, the corner down left, you see the procedure for both monotonic and cyclic loadings. Here we tested the monotonic first, and based on the monotonic results, we constructed the procedure, we designed the procedure for the cyclic loading. So after testing all the specimens, we observed a very interesting phenomenon, and that is the type of the cracks that appeared on the specimens after the test, which is based on the bond failure mode. We observed that for those specimens that had a splitting failure, you can see on the top picture, the cracks start from the center of the rebar and goes to the cover and the sides. It showed that when splitting failure happens, which if you remember is the sudden failure, in simple words, the concrete detaches from the rebar. But when the failure mode is pull out, the cracks are around the rebar and they are not connected to the rebar, meaning even after the rupture, there is still some confinement for the rebar, and that helps to have that flexible or gradual or smooth failure. Here I put different patterns for each failure mode. You see these are the top splitting patterns. Even though you might think they are different, but they are actually following the same rule, that they are connected to the rebar for the splitting. And for the pullout, you see, even though like they can form differently, the cracks, but still they have the same cracking pattern and the rule that I mentioned previously, that are not connected and still the concrete attached to the rebar. And after the testing, we developed two different models for this paper. One model can predict the failure mode of a specimen. It means based on the configuration of the specimen, you can tell whether the specimen or the structure is more probable to have pull-out failure mode or more probable to have a splitting failure mode. We used machine learning approaches to develop the models, but at the end, eventually, we adopted lasso and logistic classifications to be the best approach for the models, and then we picked lasso classification because it resulted in a better model in terms of accuracy. Second, we developed a model for predicting the bond strength. If you remember, I said that there are some research on bond strength prediction, but the model that we developed, apart from being probabilistic, it also includes the failure mode of the bond in the prediction of bond strength, meaning our model is able to tell us if the structure is going to fail under pull-out failure, what is going to be the bond strength, and if it's going to fail under splitting failure, what is going to be the bond strength. So for the bond strength prediction, we use nonlinear multivariable regression method. Using the lasso and logistic classification, the developed model is, as you can see in this slide. I don't want to elaborate on this model because we already published the paper on this model, but it's worthy to note that the model includes the structure parameters such as cover size F prime C, rebar diameter, and transverse stirrups, and also corrosion. Also, you can see it also considers, I can show you here, being the loading type, which is monotonic or cyclic, and also corrosion, F prime C, and C over D. But for the bond strength prediction, firstly, 4 explanatory functions are defined that showed good correlation in different literatures with the bond strength, H1, H2, H3, and H4, as you can see here. H1, you can just know that H1 considers the confinement effect due to cover. H2 considers the confinement due to the effective width. H3 considers the confinement due to the stirrups, and H4 considers the embedment length. Then each of these 4 explanatory functions are interacted with the corrosion term. You can see here it's in a form of exponential. And then also 2 dummy variables, the failure mode and the loading type, are interacted with each explanatory functions. And then the results, the bond strength, which is like the tau bond strength, the shear bond strength, is normalized to a square root of F prime C, and is in the form of ln. So before I show you the final model for bond strength prediction model, it's good to know that for the model we used 132 data of our own, the experiment that we had. We also used 240 data from the literature. For the validation, the assumptions of homoscedasticity and normality is used, and also diagnostic plots are used. In this slide, I just wanted to show that why we use multivariable regression and what are the advantages, but your takeout could be that multivariable regression we can use and implement it later in reliability analysis, and also we can calculate the confidence intervals of the prediction. And in this slide, you can see the final model as a result of the nonlinear regression. For the bond strength, I want you to pay attention to the terms that are in the model. We see we have all H1, H2, H3, and H4, and also the corrosion term. And here in this figure, you can see it shows the dots are lined within the positive and negative standard deviation, and it's all scattered, and it showed a very acceptable and satisfying accuracy. So after we developed the model, we used the model for bond strength in a case study. Our case study includes 2 reinforced concrete beams that we adopted from the literature. These 2 beams are laboratory experimented beams, and in order to study the behavior of the bond and also incorporate the bond strength into the reliability analysis of these 2 beams, we adopted an analytical procedure, as you can see in this slide. This analytical procedure, I don't want to get into the details because then you might be confused, but I would like to explain how it works. So it basically calculates the displacement of the midspan of a beam, of an RC beam, with applied 2-point loading on the beam by calculating the number of the cracks that happens to the beam, and also by calculating the spacing of the cracks between the beam. As you can see in this equation, the total deflection of the beam is basically the accumulation of the strain for each crack element. Here, these are the procedure that is used in the whole process of calculating the beam deflection. I just wanted to highlight our bond strength model that is used to calculate the maximum capacity of the beam. And also you can see that in the procedure, in the procedure of the moment or force deflection diagram, we use compatibility and equilibrium, and also the stress strain distribution over the beam. You can see generally this is like the basic of like RC beams that we have. We have the force, we have the moment, we can calculate the elongation, and when we have the elongation, as you remember on the previous slide, we can calculate the slippage, and then we can calculate the total displacement of the midspan. And in this slide, you can see the result of the procedure. So the result of the procedure, if you remember, was the load and displacement. So it gives us the load versus displacement diagram. The solid line is the actual load displacement that was tested in the Abdul Karim literature that we adopted, and we showed the picture of the beam in previous slides. And the dashed line, you can see what is the calculated displacement from the procedure. And this maximum point is the point of the failure, which is based on our developed model that predicts the bond strength, the maximum bond strength, as we can say. We can see for different values of F prime C, we tried different values of F prime C for the beam, and we saw that we are having a very good accuracy in terms of the displacement and also the maximum failure with a very good accuracy. And also remember that this beam showed a pull-out failure mode, so we used the pull-out model, bond strength model. In this slide, you can see the prediction of the procedure and bond strength model, but for a different case study beam, the second beam from Ahmad 2007. Their experiment showed a splitting failure. And in these three figures, you can see they have, instead of F prime C, we have different values of corrosion. We have 0% corrosion, 14%, and 5% corrosion. We see that our model is doing very well also in terms of having different values, different value for corrosion, and also it can predict not only the whole figure, the whole diagram matches the actual experiment. We can see the failure point of the procedure and also the bond strength model that we developed agrees well with the actual experiment. Okay, so let's review what we learned in this research. We learned that corrosion significantly changes the performance and behavior of the structure, and corrosion affect the load carrying capacity, which in terms of structures, or bond strength in terms of specimens, local bond strength. Also, corrosion affects the failure behavior of the structure, which was pull-out failure mode or splitting failure mode. And also, we learned that understanding and predicting these differences is important in design of structures. So predicting bond strength and failure mode are necessary for any structures. So when we developed the model, we showed that our model, the model that was developed in this research, showed a realistic prediction with a very good accuracy for reinforced concrete beam specimens. And at the end, I would like to thank you for listening to my presentation. I know it's not normal to have these type of presentations or having, especially like in a conference that we are used to having social cues, but it's hard to have that in virtual conferences. But I would be more than happy to receive questions. If you have any questions about my research, please reach out to me, and thank you so much for the time that you listened to this presentation.